¡Apártate, cabeza de balón!
Without further ado, let's learn about second law of thermodynamics and thermal energy reservoir. So what is exactly second law of thermodynamics? Second law of thermodynamics observes that energy has quality as well as quantity, and actual process occur in the direction of decreasing quality of energy. For example, a cup of hot coffee left on the table eventually cools. A cup of cold coffee in the same room never gets hot by itself. The higher temperature energy of the coffee is degraded or transformed into a less useful form at a lower temperature once it is transferred. A thermal energy reservoir is a body with a very large thermal capacity. A distinctive characteristic of thermal energy reservoir is that it can supply or receive large amount of thermal energy without experiencing any change in temperature. In actual thermodynamic system, expansive bodies of water such as oceans, lakes, or rivers are considered thermal energy reservoir because of their large masses and high heat capacities.
What is the Carnot cycle? The Carnot cycle is a theoretical thermodynamic cycle that describes the operation of a perfect heat engine. It consists of four reversible processes, which are isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression. The Carnot cycle is used as a standard for comparing the efficiency of real heat engines and serve as a theoretical upper limit for the efficiency of any heat engine operating between two temperature reservoirs. It was developed by French engineer SIDEK Carnot in 1824 and is an important concept in the study of thermodynamics.
So the number one is reversible isothermal expansion. What is reversible isothermal expansion? It is a process where there is a rise in a volume at a constant temperature. From the example in the slide, at the beginning, which is state 1, the gas temperature is TH and the cylinder head is in direct contact with a source that is also at TH. The gas is permitted to gently grow, altering the surrounding area. Then, the temperature of the gas tends to drop as it expands. However, some heat is transported from the reservoir into the gas and the temperature of the gas rises to T as soon as the temperature drops by a negligible amount of T. As a result, TH maintains as a consistent gas temperature. This is a reversible heat transfer mechanism because the temperature of differential between the gas and the reservoir never rises over a differential amount dt. It keeps going until the pistons gets to position 2. The total quantity of heat that is sent to the gas during processes, which is QH. The second one is reversible adiabatic expansion. Did you know what is reversible adiabatic expansion? It is an idealized thermodynamic process that is adiabatic and in which the work transfers of the system are frictionless, which are there is no transfer of heat or matter, and the process is reversible. So, based in the slide, it has said that temperature will drop from TH to TL. So here how it will shows. In order to make the system adiabatic, the reservoir that was in contact with the cylinder head is removed at state 2 and replaced with insulation, and then the gas keeps expanding gradually, changing its surrounding as it does. So, until its temperature falls from TH to TL, which are at state 3. And then, the process is adiabatic and reversible, since it is assumed that the piston is frictionless, and that the process is called quasi-equilibrium.
Let me explain more about reversible isothermal compression. In this process, the low temperature remains constant. As shown in the diagram, it describes a reversible isothermal compression process 3 to 4, where the gas is brought into contact with a sink at lower temperature. As the gas is compressed, the temperature tends to rise, but any temperature increase is immediately offset by heat transfer to the sink, keeping the gas temperature constant at low temperature. This results in a reversible heat transfer process continuing until the piston reaches state 4. The amount of heat rejected from the gas during this process is denoted as QL. The last process is reversible adiabatic compression. In this process, the temperature rises from lower temperature to higher temperature. As shown in the diagram, the reversible adiabatic compression process 4 to 1 involves compressing the gas in a reversible manner after removing the low temperature reservoir and insulating the cylinder head. This process causes the temperature of the gas to rise from lower temperature to higher temperature, returning the gas to its initial state, which is state 1, and completing the cycle.
This is a PV diagram of the Carnot cycle. The area under curve 1 to 3 is the work done by the gas during the expansion part of the cycle, and the area under curve 3 for 1 is the work done on the gas during the compression part of the cycle. The area enclosed by the path of the cycle, area 1, 2, 3, 4, 1, is the difference between these two, and
the Carnot heat engine cycle just described is a totally reversible cycle. Therefore, all the process that comprise it can be reversed, in which case it becomes the Carnot refrigeration cycle. This time, the cycle remains exactly the same, except the direction of any heat and work interaction and reverse. Heat in the amount of QL is absorbed from the low temperature reservoir. Heat in the amount of QH is rejected to a high temperature reservoir, and a work input of W net in is required to accomplish all this. The PV diagram of the reverse Carnot cycle is the same as the one given for the Carnot cycle, except that the direction of the process are reversed, as shown in the picture. Carnot refrigeration cycle.
Next, we want to explain about the Carnot principle. The Carnot principle uses the second law of thermodynamics that puts limits on the operation of cyclic device as expressed by the Kelvin-Planck and Clausius statements. Kelvin-Planck and Clausius state a heat engine cannot operate by exchanging heat with a single reservoir, and a refrigerator cannot operate without a net energy input from an external source. Did you know that from the statement we can get two principles known as Carnot principle? The first one is the efficiency of an irreversible heat engine is always less than the efficiency of a reversible one operating between the same two reservoirs. So, for the second one is the efficiency of all reversible heat engines operating between the same two reservoirs are the same.
The first Carnot principle is the efficiency of an irreversible heat engine is always less than the efficiency of a reversible one operating between the same two reservoirs. So let me explain to you about the first principle. In violation of the first current principle, we assume that the irreversible heat engine is more efficient than the reversible one, which is NTH irreversible greater than NTH reversible, and thus delivers more work than the reversible one. Now, let the reversible heat engine be reversed and operate as a refrigerator. This refrigerator will receive a work input of W reversible and reject heat to the high temperature reservoir. Since the refrigerator is rejecting heat in the amount of QH to the high temperature of reservoir, and the irreversible heat engine is receiving the same amount of heat from this reservoir, the net heat exchange for this reservoir is zero. Thus, it could be eliminated by having the refrigerator discharge QH directly into the irreversible heat engine. Now, considering the refrigerator and the irreversible heat engine together, we have an engine that produces a net work in the amount of W irreversible minus W reversible, while exchanging heat with a single reservoir, a violation of the Kelvin-Planck statement of the second law. Therefore, our initial assumption that NTH irreversible greater than NTH reversible is incorrect. Then we can conclude that no heat engine can be more efficient than a reversible heat engine operating between the same reservoirs.
For second Carnot principle also be proved in a similar manner with the first Carnot principle. But this time, let us replace the irreversible engine with another reversible engine that is more efficient and thus delivers more work than the first reversible engine. By following through the same reasoning, we end up having an engine that produces a net amount of work while exchanging heat with a single reservoir, which is a violation of the second law. Therefore, we conclude that no reversible heat engine can be more efficient than a reversible one operating between the same two reservoirs, regardless how the cycle is completed or the kind of working fluid used.
Now, let's move on to the last part on this topic. Let's answer the tutorial question to understand more. The first question, what are the four processes that make up the Carnot cycle? There are four processes that make up the Carnot cycle, which are reversible isothermal expansion, reversible adiabatic expansion, reversible isothermal compression, and the last one is reversible adiabatic compression. Second question, what are the two statements known as the Carnot principle? There are two statements known as the Carnot principle, which are, the first one is first Carnot principle. The efficiency of an irreversible heat engine is always less than the efficiency of reversible one operating between the same two reservoirs. Second Carnot principle. The efficiency of all reversible heat engines operating between the same two reservoirs are the same.